Hello, welcome to this talk on the paper Bounds for Synchronizing Markov Decision Processes, which is a joint work with Marie van den Bogaard. So let me start with a simple example of a Markov chain. It's a directed graph where the edges are labeled with probabilities in such a way that in every vertex, the sum of the probabilities of the outgoing edge is equal to 1. So if there is no label, it means probability 1. So for example, from Q1, we have probability half to go back to Q1 and probability half to go to Q2. From Q2, we go to Q3 with probability 1 and so on. So this is a finite state stochastic process which defines a probability measure over sets of infinite paths. And the intuition is that the graph represents a model of a system, and the path and infinite paths corresponds to an execution of the system. And so we are interested in knowing the probability that an execution of the system satisfies a certain property or belongs to a certain set. For example, the set of all paths that visit Q3. So the probability that an execution satisfies Q3 is exactly this value. And in this example, it is equal to 1. So this is the traditional semantics of Markov chains that is used in verification and that has been studied a lot. Now, in this talk, we will take a different view where we consider that a Markov chain generates a sequence of probability distribution. And what is a probability distribution in this case? It's a function that goes from that maps every state of the Markov chain, so Q is a set of states, to a value between 0 and 1. And this value is the probability mass in that state. So we can represent this as a vector where each entry corresponds to one state of the system. And initially, we are in Q1, so all the probability mass is in Q1. So the vector is 1, 0, 0, 0. All the probability mass is in Q1. Now, after one execution step, the probability in Q1 is split between Q1 and Q2, and we have half, half, 0, 0. That's the next distribution. Now, if you do one more execution step, the probability half in Q1 is again split between Q1 and Q2, so you get 1 quarter, 1 quarter. And from Q2, it is transferred to Q3. So this is now a deterministic process, because if you give me a distribution, x, y, z, t, there is a unique successor, which is deterministic in some sense, and it is obtained by multiplying this distribution with the transition matrix of the Markov chain. So it's basically a linear transformation in this case. So the counterpart of having a deterministic process is that it's now infinite state. The distributions are all different along the sequence, so there is really infinitely many different distributions. Now, what is the interpretation for this view? Well, imagine that this system, this Markov chain represents the behavior of some bacteria. And imagine that we have a huge number of identical copies of those bacteria. And we have so many that we consider it as a continuum. Then a distribution will tell for every state what is the percentage of the bacteria that are in that state. For example, this distribution says that in Q3, 1 quarter of the bacteria are in Q3, and 1/2 of the bacteria are in Q4, and so on. So it's a bit like in chemistry, where you don't count the number of molecules in your system, but you talk about the concentration of a substance, of a molecule. And here it's the same thing for bacteria. So note that is a very naive model of bacteria and a naive approach to problems in biology. So it's only loosely inspired by biology and doesn't have the ambition to solve any real application in biology yet. Still, we could be interested in programming those bacteria. And for that, we need a little richer model where there are stochastic transitions like in Markov chain, but also control actions where we can influence the behavior and control the behavior. And this is called now a Markov decision process. It has a transition relation that looks like this. Given a state and an action, there will be a distribution over the successor states. So for example, here in Q1, we have two possible actions, A and B. If we choose A, then with probability half, we go to Q1, and with probability half, we go to Q2. If we choose B, then we go straight to Q4. And if there is no action, it means the action is irrelevant. We anyway take this transition. Now, to control this system, we use a control program, which in biology would take the form of a virus in the biological sense. And formally, what it is a function that tells, given the current execution of the system, the sequence of states that have been visited, what is the distribution over the actions that I want to execute. So to keep full generality, we allow randomized choice of action. So now this virus can be duplicated by biologists, and so it will attach to the bacteria. And now once the virus is attached to the bacteria, it will control the actions, and therefore it will be a purely stochastic process that generates a sequence of distributions over the state space of the bacteria, so the state space Q, but it is parameterized by the control program sigma that we also call strategy in the rest of the talk. So now the question is, what do we want to achieve with this control program, with this strategy? And well, the kind of objective that we will consider are called synchronizing objectives. And it is illustrated here with the state Q3, which imagine is a fluorescent state, which means that when the bacteria are in that state, they will emit a little flash. Now, if only a few bacteria are in Q3, the flash will be almost invisible. So what we would like is that all the bacteria, or almost all the bacteria, are in Q3 at the same time. And that's the idea of synchronization. All copies of the system will be in the same state at the same time. So in the sequence of distribution that is produced, we will say that it is eventually synchronizing in a set of target states T. So here T is just Q3. Well, it comes in two variants. Either surely if, voilà, all the probability mass is in T at some point. So there is a point in time where the probability mass in T is equal to 1. That would really mean all the bacteria are in T. Now, this is typically difficult to achieve in a stochastic system. For example, here, if you imagine that you start from Q1, if you would play A even many times, there will always be a little bit of probability that stays in Q1 and that will never be in Q3. And if you play B, it will certainly also not go to Q4. Sorry, not go to Q3. So achieving all the probability mass in Q3 might be a bit tricky and a bit difficult to achieve. So that's why we will consider also a slightly weaker version of the eventually synchronizing objective, which we call almost surely. And it asks that the supremum over time of the probability mass in T is equal to 1, which intuitively means that the probability mass in T can be arbitrarily close to 1, but not necessarily equal to 1. I mean, if it is equal to 1, it's good, but it's sufficient that it can be arbitrarily close to 1. So this definition, we call it eventually synchronizing because it was defined before. But we can think of it as synchronizing once, like a reachability kind of objective. Now, related to this, there is a natural definition of synchronizing infinitely often, which was called weakly synchronizing, and where we ask, okay, in the sure version, we ask that the probability mass in T is equal to 1 infinitely often. So it means for every position, there is a position later where the probability mass in T is equal to 1. Again, this is something that might be difficult to achieve. So we will consider a weaker version where we call that almost surely weakly synchronizing, where we require that the lim sup of the probability mass in T is equal to 1, which intuitively means that the probability mass in T can be arbitrarily close to 1 infinitely often. Now, there is some relationship between synchronizing once and synchronizing infinitely often. For example, we have this equivalence, which is true for every sequence of probabilities. The supremum of a sequence is equal to 1 if and only if either at some point is equal to 1. That's one way to satisfy it. Or we get closer and closer to 1 in the long run, and that means the lim sup is equal to 1. So this is a relationship between these two notions, and it means that typically when we can solve one objective, say synchronizing infinitely often, it will be very easy to solve then also the synchronizing once, because this condition here will be relatively easy to also to deal with. Now, this definition, they use value functions that are the supremum and the lim sup. We can have analogous definitions for inf and lim inf, which corresponds to the intuition that we would want synchronizing always, which is the dual of once, or synchronizing always from some point on, which is the dual of infinitely often. Okay, now we can define the type of questions that we are interested in this paper. And we'll illustrate it with weakly synchronizing or synchronizing infinitely often. So for a Markov chain, I would ask, is my Markov chain, a given Markov chain, almost sure weakly synchronizing? And this means what? This means the lim sup of the sequence of distribution of the mass of probability in the sequence of distribution in T is equal to 1. Remember that the sequence of distribution in a Markov chain is unique. So there is just this distribution, and we are interested in the mass in T and the lim sup being equal to 1. Now, in a Markov chain, in a Markov decision process, what we would ask is, well, the natural question is, does there exist a strategy or a control program to ensure that the lim sup is equal to 1? Now, there is a dual question, which is to ask whether all strategies ensure that the lim sup is equal to 1. So the existential question has been considered before, and it's been shown to be p-space complete. So we are interested in knowing the complexity of the question for Markov chain and the universal question for MDP's Markov decision process. So this universal question here, we will try to turn it into an existential. And so for that, we rewrite it as the negation of exist sigma of the negation of lim sup is equal to 1. So lim sup smaller than 1. And this is equivalent to lim inf of the complement is greater than 0. And this leads us to define questions in existential form where it says exist sigma and then some function is greater than 0. And then we can define it for lim inf, but we can also define it for lim sup, for inf, and for sup. And this we call boundedly winning. So this is one new mode of winning. And I summarize here the winning modes that we consider. So there is surely and almost surely that we have already presented. So I will illustrate it for synchronizing infinitely often. So I repeat that surely is the fact that infinitely often the probability mass is in T. Almost surely means the lim sup of the probability mass is equal to 1. Now there is the limit sure mode that has been defined before also, where we don't ask if there exists a strategy, we want to know if the supremum of our strategies gives us the value 1. It's analogous to the value problem in games. So you may achieve it by a sequence of strategies rather than by a single strategy. Now the new winning modes that we will consider and that we define in this paper is, first of all, boundedly that I just mentioned before. So it says, does there exist a strategy such that the lim sup of the probability mass is greater than 0? And then there is the positive version where we ask whether there is a strategy to ensure that infinitely often the probability mass is just positive, just there is some probability mass in T. Now you may wonder why there is no third version where we replace the exist sigma by a supremum, and this is because it's equivalent to the exist sigma. So the supremum sigma of a function is greater than 0 if and only if there exists sigma, such that this function is greater than 0. So that's why the supremum doesn't give a new winning mode here. So now these are the definitions for weakly synchronizing with lim sup, but we can of course have analogous definitions for sup inf and lim inf. So this gives 20 winning modes. But the sure, almost sure, and limit sure have been studied before. So we will only in this paper address the bounded and positive modes. Now, to illustrate the interesting properties of these winning modes, I will consider the lim inf, which is the dual of the lim sup. And so it requires that there exists a strategy such that the lim inf is greater than 0, or there exists a strategy such that from some point on, there is always some probability in T. So this always from some point on synchronizing. So for positive winning, this is relatively simple. So what I claim is that a strategy to achieve positive winning could play all actions uniformly at random. And so this is an example of an MDP, which is actually a graph because all the transitions are non-stochastic, where we have two actions A and B. And the idea by playing all actions uniformly at random is that we will spread the probability maximally, and we will ensure maximal support of the distributions, which means that if this strategy, if there is a strategy to ensure that there is some probability in T from some point on, then the strategy that plays all actions uniformly at random will certainly ensure that, because it will ensure maximal support of the distributions in some sense. So here you can see that. So I removed the the actions that are not relevant. Only in P1 there is a relevant choice of action, and the target is P1 and R2. So imagine that we start in Q0, and I want to see if this strategy is positive winning. So I just track the support of the distribution. So initially it's in Q0, then it goes to P1 because it's transition. Now it will split between P2 and R2, and then it will be in P1 R1, P2 R2, P1 R1, P2 R2. So the support will always contain an accepting state from some point on. So it will be indeed positively winning. But this strategy is not boundedly winning because the probability mass in P1 down here will vanish, right? It will be transferred slowly to the R component somehow. Yeah, like this. So it's vanishing, and so it's not going to be to ensure that the limit is greater than 0. The limit will actually be 0 at those steps where the support is in P1. F1. So for boundedly winning, we need a slightly more complicated strategy, but not so much more. So just what we will do is look at these components, which are the n components, but in case of a graph, it's just a strongly connected component of the system. And indeed, playing all actions uniformly at random, which is the first phase here, that's a good idea to reach maximal support, and we can do that initially. So in the first phase, we do that. But then, in order to avoid that the probability is transferred from one component to another, once we have reached some sort of the maximal support, we are going to play in such a way to stay in the components where we are. So we are going to play uniformly all actions that stay within the current component. And this means that in phase 2, we are not going to play the action B here. Only the action A will be played. And so this will ensure that this mass of probability of a half that we have in these two states will be non-vanishing. It will stay lower bounded, like this. So now that we have an idea of what should be the winning strategy, we can now implement an algorithm to decide if the condition is satisfied, if there exists a strategy. So for positive winning, the only thing we need to do is to fix the strategy that plays all action uniformly at random, and then check whether this condition is satisfied, whether from some point on we intersect with T. So let's consider the outcome of the uniform strategy and write it D0, D1, D2, and so on. So we are only interested in the support at this point. So we can write SI, the support of the distribution DI, and we can see that this sequence is also deterministic in the sense that given a support, the next support is uniquely determined. And also the support takes value from a finite set, the subset of the state space. And therefore this sequence will be ultimately periodic. It is deterministic over a finite state space. Now, the condition we want to check is that each of these supports intersect with T as a non-empty intersection with T from some point on. And we claim that it is sufficient to have a non-empty intersection over the periodic sequence of this ultimately periodic sequence. And this means that if you check non-empty intersection for all indices between 2 power n and 2 power n plus 1, you are sure that you cover an entire period of this sequence. Therefore, this is the condition that we need to check. And this can be checked in co-NP, in the sense that we can guess an index that violates this property. So we guess an index between 2 to the n and 2 to the n plus 1. And what we need to do is to compute the support at position I. And to do that, we need to compute the transition matrix power I multiplied by the initial distribution. But since we are interested only in the support, we can use, instead of really the transition matrix of the system, the Boolean version, where we put a 1 whenever the probability is greater than 0. So it's just a Boolean matrix, and we need to compute the power I. So I now is a huge number, but we can achieve this in polynomial time by successive squaring. Then it will be logarithmic in I, so linear in n, the size of the state space. And so now this is a co-NP algorithm to check positive winning. Now, what about boundedly winning? Well, it's not very different, because the only thing we need is that the support intersects with T in an n component, because then we will be able to keep it there by the second phase of the strategy. And so we need to check the same condition as before, just intersected with the union of all n components, which also can be computed in polynomial time. So we also have a CoNP algorithm for this question. So this gives us the CoNP upper bound for the universal question of lim_sup, which is equivalent to the existential question of lim_inf. So it also gives the upper bound for Markov chain. Of course, it's a special case. Now it can be proved that, and this we do in the paper, that for Markov chain it's CoNP hard. So this becomes CoNP complete for Markov chain and therefore also for MDPs. And also in the paper, there are other results related to bounds. So essentially when we were interested in the case where the existential question doesn't hold, so when the negation holds, so it's not true that there exists a strategy to ensure the lim_sup, then in fact this means that for all strategies the lim_inf of the complement is greater than 0. And in fact it was known that there is a bound, in the sense that there is we can compute a bound such that for all strategies the lim_inf will actually be greater than that bound. So it's not obvious a priori that such a bound exists, but this was known. But it was not known what value this bound has, and we basically establish one value for this bound, which has this shape. So just quickly, nu0 is the smallest positive probability in the initial distribution, and nu is the smallest probability in the MDPs, and is the size of the state space. So we have this uniform bound, and we have it also for the other objectives. So this is almost the end of my talk. I would like to acknowledge Masashiro Mamadi for preliminary discussions about this problem that helped us. And this is the end of my talk. So thank you for your attention.